Well, good morning. This is 11 o'clock on Tuesday, the 19th of September, 2017. This is supposed to be linear algebra class. The trouble is I'm the only one in the room. Oops, I did something too soon there. No, I didn't. I'm recording. Sorry about that. So I do have a couple of announcements. One is fairly major, okay? I wish you were here to hear it, so I'll probably repeat it every time someone comes in, if anyone comes in, okay? But let me say it now to begin with. Last week, the Vice President sent around a memorandum, and we were supposed to print it off and read it to you in class. My printer's not working because my cartridge is dead. I ordered one back in August, and it still hasn't gotten here. And I printed just about everything, shaken it and done everything I can. It just keeps getting lighter and lighter, so I didn't even bother to print it. It just is in too bad a shape to even read. But let me tell you the essence of it. The Vice President's email stated that as of tomorrow, Wednesday, the 20th, any student who has not completed payment for a class will be removed from the roll. Okay? And supposedly today I'm only calling from the registered roll, and then anyone who's not a registered student, your name doesn't get called. Well, there's only 2 of you on the roll, so it would be pretty obvious. I think you know if you have a completed payment. The deal is, if you haven't, please complete payment today or tomorrow. Please complete payment today or tomorrow. Now, let's just say that something's up. You're waiting on a scholarship, your company, Pell Grant paperwork, I don't know what it is. For some reason, you're waiting, you're ready to pay. As soon as you get this last little bit, whatever it is, done, you're able to pay. Well, if that's the case, please go by the cashier's window or the business office and let somebody know that, okay? Let them know what your situation is, why you haven't paid so far, that you are fully, totally intending to pay, you just got thus and so left to do, or whatever, and make sure they know that. They may be able to put a flag on your account and therefore not remove you from the roll. But even if they can't, usually if you can complete payment fairly soon, then they will let you back into the class. I don't know if they're going to this time. Like I said, I don't have the thing in front of me. I can't remember if it had any specifics there. The deal is, if you can't pay by today or tomorrow, please let somebody know that, okay? But try to get it done today or tomorrow. That's the best thing to do, okay? So I guess, okay, the other thing, if you are, and I know at least one of you are going to participate in the math team, I assume that maybe we've had several delays having to pick up somebody, pick up a car, or the meeting being called or something like that. But unless there are any other delays, we'll start having our practices tomorrow on Mondays and Wednesdays, starting sometime after 3:15 and ending sometime before 4:45, okay? We go as long or as short as you want to do it. But hopefully we'll get started tomorrow on that. Here in this room, 2:55, 3:15 or later until 4:45 or earlier. Okay. And then the only other thing is normally on Fridays I have office hours 7:45 to 11:45. However, this coming Friday, they've called a meeting, but they've called it for 12:30, okay, which means actually I'll be there longer than my normal office hours. So my office hours will extend from 7:45 until somewhere around 12:15, 12:30, somewhere in there. I just have to leave soon enough to get to the meeting by 12:30. So I'll be on campus a little longer than normal, not shorter. Okay, office hours a little longer, not shorter. Okay, I guess we're ready to go then. We're in Chapter 2, Matrices, 2.1 Operations Matrices, and we had just started talking about matrix multiplications, okay? And basically, I think we already started the process. You go across a row and down a column, across the row of the first matrix, down the column of the second matrix for the, say, the ijth entry of the product matrix. You take the ith row of the first matrix times the jth column of the second matrix. By the way, that means that the number of columns in the first matrix must equal the number of rows in the second matrix, so you'll have the same number of elements to multiply and add. And it doesn't matter how many rows are in the first one or how many columns in the second one. It's just that the number of columns in the first must equal the number of rows in the second. But then your product matrix is going to be the number of rows in the first matrix by the number of columns in the second matrix. Okay. So let's actually do one, a very easy one. I've got my pen set up. Let A equal 1, 2, 3, 4. Very creative matrix here. 1, 2, 3, 4. And B be the matrix 0, 1, 1, 2. Okay. Now, the first thing to do is add the two matrices. What's A plus B? Hopefully, you can do that in your head. 1 plus 0 is 1. 2 plus 1 is 2. 3 plus 1 is 4. 4 plus 2 is 6. Okay? There's A plus B. Second thing it says is to add B plus A. Hopefully you can do that in your head. 0 plus 1 is 1. 1 plus 2 is 3. 1 plus 3 is 4. And 2 plus 4 is 6. Okay? Guess what? If I could add. I think I was multiplying here. Go back and do that second entry again. 1 plus 0 is 1. 2 plus 1 is 3. Okay. So guess what? A plus B is equal to B plus A. So, at least by this example, it appears, and it is indeed true, that addition of two matrices, as long as they're the same size. This is a 2 by 2 added to a 2 by 2. Sure, you can do that. 2 by 7 to a 2 by 7, you can add that. 7 by 2 plus a 7 by 2, you can do that. 2 by 2 plus a 3 by 2, you cannot do that. 2 by 2 plus 2 by 3, you cannot do that. To add two matrices, they have to be the same size, and then if they are the same size, it doesn't matter the order that you add them. Okay. But the next thing they ask us to do is do AB. In other words, multiply these two matrices. Okay, this again is pretty easy, especially since you've got a 2 by 2. Hey.
I'm here at the top class, but I only be here on the game one time because I do some work. But since I just changed my schedule around, they said that to come ask you if I could. Do you think I could catch up?
I'm sorry?
It's on the ask you. Do you think I could?
Okay, let me pause this. Sorry about the interruption. A student just walked into the classroom and started talking with me. I got to shut down, but she just kept talking, so I had to shut it down so I wouldn't be recording all that. So let's multiply these two. Well, this is a 2 by 2 times a 2 by 2. Yes, you can multiply those two. So 2 by 2 times a 2 by 2. Wipe out the first, and you're going to get a 2 by 2. So 1, 2, 3, 4. So for the first entry, first row, first column, that's a 1, 1 entry, multiply the first row of this one by the first column of that one. So that would be a 0 plus 2 is 2. The 1, 2 entry will be the first row of A, second column of B. B1 plus 4 is 5. And then the 2, 1 entry, second row by first column, would be 0 plus 4 is 4. And first or second row by second column, the 2, 2 entry here, would be 3 plus 8 is 11. Now let's do B times A. And again, 2 by 2 by 2 by 2, you'll get a 2 by 2. But now we're doing first the rows of B by the columns of A, because we're doing them in reverse order. Okay? So that would be 0 plus 3, that would be a 3. The 2, 2 entry would be first row by second column. That would be a 0, 4. Then the 2, 1 entry here would be second row times the first column. 1 plus 6 is 7. And the second row by the second column for the 2, 2 entry here would be 2 plus 8 is 10. Okay. Now, if you glance at those two, you'll see that nowhere close are these multiplication is not anywhere close to being commutative for matrices in this example and in most examples. There are a few, and there are very special matrices for which AB is equal to BA. When you run into one, take special note of it. But in general, if you can multiply the two matrices A and B, and you can also and you can multiply the other way, B times A. By the way, the size requirements there would be A, let's see if I can say this right. If A is an M by N matrix, B has to be an N by M matrix. Okay? Because if you can multiply them both ways, that means the middle two of the first, M by N, M by N by M by M, that would give you an M by M matrix, or an N by M by M by N, that would give you an N by N matrix. So obviously, there are ways you can multiply, commute, and not even get the same size matrix, you know. For square matrices, yeah, they get the same size, but they don't get the same numbers, the same entries. So in general, matrix multiplication is not commutative. For a few very special square matrices, it may be commutative, and those are very special situations. Okay, let's clear that out of the way. I'm sorry about my throat. I should have said this earlier. I went to the UAB game on Saturday and yelled too much, so my throat was a little rough. Then I talked for 6 hours yesterday. I almost didn't have a voice at the end of the day. I had a meeting last night. I could barely talk at it, and then today it hasn't started much better than I left off last night. So sorry about the throat. Hopefully it'll get better as the week goes on, but boy, today is not great. So let's do example 5, matrix multiplication. Here is the A part of 5. Here's a matrix, 1, 0, 3, 2, negative 1, negative 2. And we want to multiply that by the matrix, negative 2, 4, 2, 1, 0, 0, and negative 1, 1, negative 1. Now, the first question, can you even multiply those? Okay? Well, this is a 2 by 3. This is a 3 by 3. So sure enough, the inner two numbers are the same. Wipe them out. Your answer is going to be a 2 by 3. All right, let's multiply them and see what they get. The book actually gives them to you, but why? Let's go on and practice our multiplication. This is the 1, 1 entry, so you take the first row of the first matrix by the first column of the second matrix, 1, 1, and that would give you -2, 0, -3. That would give you a -5. The 1, 2 entry would be first row of the first one times the second column of the next one. That would be 4, 0, 3 would be 7. The 1, 3 entry, first row here, third column here, 2, 0, -3, that would be a -1. Okay? The 2, 1 entry here would be second row of this, first column there, that would be a -4, -1 would be -5, plus 2 would be a -3. The 2, 2 column, 2, 2 entry, would be second row times second column, would be 8, 0, I'm sorry, -2, that would be 6. And then the 2, 3 entry would be second row by the third column, that would be 2, 0, 2, 2 and 2 is 4. Really high level math today. -5, 7, -1, -3, 6. Whoa! I'm sorry. 4, 0, 2 is 6. 4 and 2 is 6. Sorry. I can't multiply today either. Okay. 6, 3, -3, 6, 6. Take your time with matrix multiplication. If you get rushing too much, you usually will make a mistake. All right? Oh my goodness gracious. I don't know why my back is aching like crazy today. I didn't do much yesterday. I did some over the weekend, but I don't know why back's hurting today. So let's do the B one. The B one is 3, 4, -2, 5 times 1, 0, 0, 1. Hopefully you remember what that's called. The I2, 2 by 2 identity matrix. Okay? The question is, can you multiply them? Well, this is a 2 by 2 by 2 by 2. Of course, the inner numbers are both 2's. Your product is going to be a 2 by 2. All right. Top left entry here is the 1, 1 entry. So you take the first row of the first one by the first column of the second one. 3 plus 0 is 3. The 1, 2 entry would be first row by second column. 0 plus 4 is 4. The 2, 1 entry would be second row by the first column. -2 plus 0 is -2. And the 2, 2 entry would be second row by the second column. My goodness, I can hardly breathe. That would be a 0 plus 5 is 5. Now, what do you notice? You get the first matrix reproduced. And maybe now you see why this is called the identity matrix. Because when you multiply any matrix that's multipliable, that the size is right, you can multiply by a given identity matrix, you're going to just reproduce the first matrix. It gives you identically the first matrix all over again. Okay. I think I'm going to need more room. I can squeeze C in, I think. Even over here, I believe. here is C. That is a 1, 2, 1, 1 multiplied by a negative 1, 2, 1, negative 1, negative 1, 2, 1, negative 1. Okay, let's see what happens if you multiply those two together. Well, this is a 2 by 2 multiplied by a 2 by 2. So the set of 2's go out, so you should get a 2 by 2. Okay. My head started hurting in the last class, and then it sort of eased off. So in between classes, I went down and got something to drink. I thought I might be getting a little dehydrated. But it's coming back. It seems like everything's hurting now. So sure enough, we should be able to multiply these two together. So it should give us a 2 by 2. So for the 2, 1, 1 entry, you do first row of this one by the first column there. That would be a negative 1. Plus 2 would be a 1. The 1, 2 entry would be first row by second column. It would be a 2 minus 2 is 0. The 2, 1 entry, second row here by the first column there, would be a minus 1 plus 1 is 0. And then your 2, 2 entry is second row here, second column there, would be a 2 minus 1 is 1. Now this is interesting. Here you have two matrices that when you multiply them together, you get the identity matrix of the same size. Now they both have to be square matrices to get that, but they are square matrices, and you get that. Now, those two matrices have a special relationship. We're not there yet, but hang on to that concept. When you multiply two matrices together and it produces a product that is the identity matrix, we call these matrix inverses of each other. Okay? Another unique thing about that pair of matrix would be commutable. Okay? The others you can go back and try. Well, actually, this set is too, because the identity matrix, A times I is equal to I times A. It's all equal to A. Okay? This one is not commutable, number one, because you can't even multiply them the other way. A 3 by 3 will not multiply by a 2 by 3 at all. So, but this one happens to be one, and let's just do this quickly. If you do the other way, that's B times A. So again, it's a 2, 2 by 2 matrix. Excuse me. I'm going to try to finish this example before I go get something else to drink, and maybe something to unclear my head, because I'm really clogging up badly. And again, this happened at the end of the last class, so I went down and cleared it out, but it sure has come back with a vengeance. So we're going to use the first row of this by the first column of that one. That would be a minus 1 plus 2 is 1. And then the 1, 2 entry here will be the first row of B times the second column of A. That would be a minus 2 plus 2. That would be a 0. And then the 2, 1 entry here will be the second row of B times the first column of A. That would be a 1 minus 1. That would be 0. And the 2, 2 entry here be second row of B times the second column of A. That'd be 2 minus 1 is 1. So sure enough, those two, if you produce the identity matrix multiplying one way, then you can commute and multiply the other way. And from the previous one, if you multiply a matrix by the identity matrix of the proper size, now these have to be square matrices, then you can commute that as well by multiplying the identity matrix by the original matrix. Okay, so that gets through C. Okay, I'm going to clear the ink off of this slide. I'm going to put it on pause. And I'm having trouble talking, and so I'm going to take a cough drop, and that'll make it sound like I've got rocks in my mouth, but I've got to do something to loosen my throat.
Yeah, might be the AC.
I think it is.
Yeah.
Well, it's cooler outside than it was in the cool air.
Yeah.
But I'm also hoarse because I went to the UAB game Saturday. Yelled too much.
You was cheering?
Huh?
You was cheering?
I said, I can't hear.
I said you was cheering?
Oh, yeah.
You was going to UAB?
Yeah.
Oh, okay.
Okay. Where we were before I went down to get something to drink was on page 44, bottom of the page, example 5. I had done the first 3, A, B, and C, and now I was going to do D, which is a pretty easy one. Here is D. 1, negative 2, negative 3 times 2, negative 1, 1. Okay? First thing you ask yourself, and by the way, these are matrices. The first is called a row matrix. The second is called the column matrix. You could also call those a row vector or a column vector. Anytime one of the dimensions is only 1, it can be called a vector as well. Okay? Now, the first question you ask yourself is, can you multiply these two? What is the size of the first one?
1 by 3.
1 by 3. What's the size of the second one?
3 by 1.
3 by 1. So sure enough, the middle numbers are the same. Wipe them out. What's your answer going to be? 1 by 1, a single entry. Okay? And how do you do that? It's a 1-1 entry, so it's the first row by the first column. That's all there is.
2. 2.
Which is?
Are you adding?
Yeah.
Okay, 4. And then negative 3, which is 1.
1. Okay, that's what you got. Just the 1 by 1 matrix 1. Okay? Now, the E one takes the same two matrices, but in reversed order, 2, negative 1, 1, and multiply that by 1, negative 2, negative 3. And the question is, can you multiply those two?
Yeah.
Why? The first one is a?
1 by 3.
No, it isn't.
Oh, no. It's 3 by 1.
3 by 1. And the second one is a? 1 by 3. And sure enough, those middle numbers are the same. Wipe them out. That's going to give you a 3 by 3. Wouldn't think you could get something that big out of these two things so small. To get that 1-1 entry, we take the first row here and multiply it by the first column there. What does that give you?
2.
2. And that's all, right?
Yeah.
And the next entry is what? Oh, we got 100% attendance today. Very good. Now, how was the meeting yesterday, by the way? Oh, you didn't? We could have met then, huh?
We could have, yeah.
Oh,
Well, we can meet tomorrow.
okay. Somebody else came by for the thing. I said, well, I heard there was a meeting today. He said, oh, okay, I'll go to it. I asked him this morning. He said, I got lost. He's the best for campus person only. And he went over there and wound up in Winona High School. He didn't know how close he was to the college campus, but he said I was lost. I was on a high school.
Yeah, I'm not familiar with it.
Oh, you're not? Oh, I thought you had done some courses there. Okay, so I guess tomorrow, and from all our Monday, Wednesdays that you want to do it, from now on, meet here about 3:15 or a little after 3:15, and we'll go till a little before 4:45, right? Because that's when the class starts. Or we can stop sooner. We can start later, stop sooner, whatever you want to do. So we'll try it again tomorrow. Number 2 thing was, if you know of anyone who has not completed payment for a course, for the term, they've got to get the payment completed by tomorrow. Otherwise, after tomorrow, they will be removing people from the roll. Okay? So please let them know. If you know of anyone who hasn't done it. If they can't, go by the business office or the cashier's window and explain the situation, what you're waiting on, what the deal is. They may be able to put a flag on your account and not remove you from the roll. I don't know if they'll do that or not, but it's a possibility. But the best thing is to get paid. And then the third, this is just a minor little thing. Normally on Fridays, my office hours on the Birmingham campus, 7:45 in the morning until 11:45 in the morning. However, Friday they called a meeting for 12:30, which means I'll be there from 7:45 till 12:30. Then I'll be at the meeting, and then I'll get to come home. Anyway, that's what's going on. Okay. So, I can't remember, were you at all interested in participating in the math practices?
That's gonna have to.
Yeah, okay. I was going to say, even if you're not interested in the competition, the practices will be great things for future courses, you know. So, but anyway, let's go. Are you a pre-engineering major?
Yes, sir.
You are. One of the things that will be really good for is that FE exam, the fundamentals exam that they give shortly after you graduate or junior year sometime in there. That's large. One of those sections is largely math, and those would be great study guides. So you know things that help with that. Okay, what we're doing, Jasmine, we're doing the example 5 at the bottom of page 44, the E part. Here's 2 matrices we're trying to multiply. We've already determined this is a 3 by 1, that's a 1 by 3, so sure enough we can multiply them. The 1s go out, that gives you a 3 by 3. We did the first entry, we're about to do the second. What is the position of this one? The position.
Oh, second column. Row 1, second column.
Okay, so it's a 1-2 position. So we take the first row here, now the second column here, and that gives us
-4.
-4. That's all she wrote. So -4. Okay, what's the position of this entry here?
-6.
Now what's the position?
1 by 3.
1, 3. So you take the first row here by the third column here, and that is a -6. You following? Okay. What's his position here?
2 by 1.
Okay, so you take the
Second
row here by the first column there, that's
-1.
-1. What's the next position?
2 by
2, 2. So you take second row here, second column there, that's
2.
+2. Got the gist? What would be the next one?
2 by 3.
Which is? Okay, 3. Next.
2 by 3.
Say again.
No, 1 by 3 by 1. 3 by 1.
Okay. So what will you do?
Positive. Oh, yeah. Positive
1. Okay. Next.
3 by 2.
Okay.
Negative 2.
-2. Next.
3 by 3.
Negative 3. All right, let's see how they did. 2, -4, -6, -1, 2, 3, 1, -2, -3. Yep, they got it right. See how that works. Okay. So, we know how to do matrix multiplication. So what? I mean, what do we do with it? Well, one thing you can do with it, one practical application, matrix multiplication, is representing a system of linear equations. Now, this to me is not something to stand up and cheer too much about, because so what? I mean, but you can certainly do it. So let's go to a clean page and show what they mean. Here's our generic system of equations. A11 x1 plus A12 x2 plus A13 x3 is equal to x3 is equal to B1. A21 x1 plus A22 x2 plus A23 x3 is equal to B2. And A31 x1 plus A32 x2 plus A33 x3 is equal to B3. That's a generic 3 equations, 3 variables. Okay? Now, for what this is worth, you can rewrite that as a matrix multiplication. And that matrix multiplication will read something like this. A, X equal B. Now, the book bolds the X and the B, which means they can be represented as a vector. Now, a vector can be either a row vector or a column vector. These happen both to be column vectors. Okay? You could call those column matrices, and they are, but they still write it as bold. I can't write bold, so I'll give the vector symbol. But that stands for either a row matrix, a column matrix, a row vector, or a column vector. That's what the arrow means here. Where your A would be your coefficient matrix, right? That would be A11, A12, A13, A21, A22, A23, A31, A32, A33. Your X column vector would just be X1, X2, X3. And your B vector would just simply be B, B1, B2, B3. Okay. Now, that's the claim. Is it true? Can you even multiply these together and get something like that? What's the size here?
3 by 3.
That's?
1 by 3.
No.
3 by 1.
3 by 1. So 3 by 3. 3 by 1. The inner numbers are the same, so wipe them out. And sure enough, that gives you a 3 by 1. Well, at least the size says it's okay, right?
Yeah.
Let's see if the calculations say it is. To get the 1, 1 entry here, we do first row here by first column there. A11 x1 plus A12 x2 plus A13 x3 is equal to B1. Sure enough, that's your first equation. Second equation, A21x1 plus A22x2 plus A23x3 is equal to B2, exactly your second equation. Third entry here would be A31x1 plus A32x2 plus A33x3 is equal to B3, exactly your third equation. So sure, you can represent a system of equations as a matrix product with a result. Okay? Now, that by itself is a yay, wow, big deal. Later we'll see you can really do something with that. Okay? Now, example 6. I'm sorry if it sounds like I'm talking with rocks in my mouth. I had to take a cough drop because my throat was getting so hoarse, plus congested, plus everything else. Okay? Here it says, solve this matrix equation, AX equals 0. For that 0 is bolded, meaning it's a 0 vector, where A is 1, negative 2, 1, and B is 2, 3, negative 2. X is x1, x2, x3, sorry, x1, x2, x3. Okay, and the 0 vector that we're dealing with here happens to be the 2 by 1 0 vector, 0, 0. Not very interesting, is it? Okay. It says solve that matrix equation where that is. So you could multiply through, which is like such a pain in the neck to do, but let's do it. A times X would be, this will be a 2 by 3 by 3 by 1, so that should give us a 2 by 1, which is certainly what we got here. So let's do the first one. That would be x1 minus 2x2. You tell me the next. First row here, first column there. Plus x3 is equal to 0. Next one would be two x1, right, is equal to 0. Okay. Now, you did all that. The next thing you do, this is what's so crazy about this, is rewrite that as a matrix. Augmented matrix, 1, negative 2, 1, 0, right? 2, 3, negative 1, 0. And then you start your row reduction. What's the first thing you want to be true here? What's the first thing you want to be true there?
Make sure you got a 1.
That's the 1 there, and you got it. Good deal. So what do we want to happen next?
Make sure you got a 0.
0 below it. How do you make that happen?
2R1.
Minus 2 plus R2. Whoa, I wrote it in the wrong place. I should have written that down here. Okay? So that will be, I'm leaving my first row alone. 1, negative 2, 1, 0. And the new second row becomes 0,
7,
7? Okay, I'm sorry.
-3.
Yep. 0. Okay. Boy, what a pain in the neck that looks like it is. All right. What's the next thing we want to happen? Wait, I wrote something wrong. That's supposed to be a -2 there. See, that's a -2. I wrote a -1. So let's redo that last one. Oh, yuck. Let me do them both. All right. That was a 0, 7. That was fine. -4. Okay. All right. What do we want to happen next? Well, not yet. Yeah, you want the 7 to become a 1. Okay, how do we make that happen? Divide by 7. Okay. That will now become, again, we're only doing the bottom, 1, -2, 1, 0. And that will be a 0 still. That will be a 1. This will be a -4/7. And this will be a 0. Right? Now what do we want to happen next? You want the -2 to become a 0? Is that what you said? Yes. How do we make that happen? Okay, 2 row 2 plus row 1. Okay, so since we're using the second row, I'm going to write it down. 0, 1, -4/7, 0. Now, you tell me what the new top row will be. 1, 0. Second. Say it one more time. Okay. You got 2 times a -4/7. That would be -8/7, right? Okay. Plus 7/7. -1/7. And then I can do the last one. 0. Okay. Now, we've got our matrix. Now we have to figure out what our solution is. Well, obviously, we can deal with the x1s and x2s. We can't deal much with the x3s. So what do we name that? X3 parameter. Which one do you want? T? That's what everybody's favorite is here. Okay, so we'll let x3 equal t. Okay, what does that first row of that matrix tell you? x1 okay, so that means x1 is equal to 1/7 t. Okay, what does the second row tell you? Okay, so one set of ordered triplets would be 1/7 t, 4/7 t, t. Okay? If you don't particularly like the fractions, just multiply every one of them by 7. So that would be, another would be t, 4t, 7t. That will work too. Okay? That I find easier to work with. So 0, 0, 0 certainly will work. We knew that because this was a homogeneous equation, a system. So 0, 0, 0 is always a solution. But then another would be 1, 4, 7, and infinite number of them like that. So, what's that?
What you did right down the last step.
Okay. Because I didn't like fractional forms, I really object to them. I multiply each one of them by the least common denominator, which is 7. That makes that t, that makes that 4t, that makes that 7t. And that's just easier to work with. No fractions, it's easier to read, I think. Okay? So, they also, technically, I probably shouldn't do it as an ordered triplet like I did. They are saying, write it this way, t, 4t, 7t as a, that represents by x1, x2, x3 as a column vector, which you could write as t times 1, 4, 7. You know, by scalar multiple. Okay. And then they give a bunch of possibilities there. And we did too. We did the zeros, so 1, 4, 7. We didn't do the 2, 8, 14. That's just doubling it. -1, -4, -7. It's just infinite number of solutions. Okay. Now, if you recall back, I think it was last time or time before last, we did mention partitioning matrices. Okay? Now, everything in this section is true. And maybe you find it useful. I don't find rewriting it all that useful, but they seem to like to do it, so let's do it. Okay? So here's matrix A. Generic matrix. A11, A12, A13, dot, 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 A1, N. I think it is. Yeah. A21, A22, A23, dot, 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 to A2, N. A31, A32, A33, dot, 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 to A3, N. Dot, 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 this down, keep on going till you get to I want to expand my bracket a little bit. A M1 dot, 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 A M2 dot, 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 A M3. That M looks a lot like a 3. Let me see if I can clean it up a little bit. Goodness gracious. M3 dot, 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 everywhere, dot, dot. Okay, A, M, N. Okay, there's a matrix A, which is a M by N matrix. M rows, N columns. Okay. And here we have a vector X, column vector, and it will be X1, X2, X3, dot, 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 down to X sub N. Okay? And then we have a B column vector, which is B1, B2, B3, dot, 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 down to B sub M. Okay. On first glance, you might say, are my dimensions okay? Well, like we said before, this is an M by N matrix. That vector is a vector here is what? This one.
That's a 4 by 1, 4 by 3.
Well, it's got a dot, 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 and that's an N down there.
3 by 1.
N by 1, right?
Oh, N by 1.
N by 1.
Wow.
So this is an M by N by 1. Sure enough, the N's cancel out. We're going to write them down. This is a M by N. This is an N by 1, and sure enough, those do. And this turns out being an M by 1, and sure enough, that's what it is. MBs, okay, 1 column. Okay. So it looks like that may be multipliable to do that. Okay. Now, if you were to set this up and do this by that, which is what we're going to do, I'd rather not say it and then just say this is equal to B. You could split out and say the column vector, but this was listed as B. And you do that math there, you have A11x1 plus A12x2 plus A13x3 plus dot, dot, dot plus A1n xn. Okay, and that's equal to your B1. Okay, they don't. Well, actually, they do all these first. A21x1 plus A22x2 plus A23x3 plus dot, dot, dot plus A sub 2n. Okay. That's equal to B2. And you keep going A31x1 plus A32x2 plus A33x3. Again, those threes get really ugly, don't they? Plus dot, dot, dot plus A A3n xn. That would be B3. And then you dot, dot, dot down here, and you get A M1 x1 plus A M2 x2 plus A M3 x3 plus dot, dot, dot plus A M N getting my pen to work right. When you get right near the bottom of the page, it sort of cuts in and out. So that's A, M, N, X. Sub M. No, X sub N. M, N, X, N. Okay. That would be B sub M. Okay. And basically, if you write this just as a matrix, you got dot, dot, dots everywhere here. That is a matrix, then this is just the B matrix, and that's how the book did it. Now, here's the thing they want you to notice. Okay? That basically, this first is not a column, but it acts like a column here. These are all things multiplied by x1. It's a sub 1, 1, a sub 2, 1, a sub 3, 1, a sub m1. Everything in between times x1 plus a sub 1, 2, a sub 2, 2, a sub 3, 2, all the way up to x sub n, m2. That's another column vector. Okay? And I just don't have room. Do both of you have your books? No. Okay. Okay. I'm going to try to write in a few of them just so you'll see. Let's just do that one. This would be x sub 1 times a11, a12, or 21, a31, dot, 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 am1, plus x sub 2, yeah, a12, a22, a32, dot, 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 am2, yeah, am2, plus x sub 3, a13, a23, a33, dot, 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 a sub m3, plus, and you keep on going until you get out to x sub n, I just don't have room for it, times a1n, a2n, a3n, all the way down. Okay? And that combination is also equal to your B vector, column vector, just like that one is. Okay? Now, I'm going to go up and erase something at the top. I hope I won't need it again. It's just too small a screen to get all these huge old matrices home. And we're running out of time to boot. It's going to take me the whole day to get this erased. All right. Now, this last thing we did here, that could be written this way. X sub 1 times this column vector, I think they call it A1, don't they? Yeah, column vector A1. Just this one here, where all of your second elements is 1. Okay? Plus x sub 2 times the column vector A2, well, the second vectors are that, plus x sub 3, a sub 3, plus dot 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 plus, I wish I had room to do all these over here, x sub n times a sub n, column vector that, and that's equal to b. Okay? Well, each one of these, that would be, that one would be just equal to b1, not the whole vector b, but b1. So. Okay. Well, actually, no, if you add them all together, it's not just the one. So what I was going to say before was that B. Okay. And that's the vector B. Okay.
You said right here.
Yeah. I just didn't have time to do it.
Yeah, I know.
Just do a dot, 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 so you have x of n,
Yeah.
and then you have a1, yeah, a1, n, a2, n, a3, n, a4, n, and that becomes x. H of n, sorry about that. And that, all those added together give you your b vectors. Okay? Now that's called the linear combination of the column matrices A1 through AN with coefficients x1 through x of n, which is a little bizarre because we usually call the x's your variables and the a's your coefficients, but they sort of swapped them around. And that we're out of time, so let's stop there and we'll pick up next time. I guess we'll do the little thing at the bottom of the page, the little linear combination and column vectors. Yeah, I think we should. And then we'll do example 7. All right, we almost finished 2.1, didn't quite get it finished. Homework exercises here, do either 1 or 3 or both. Any of the odds 5 through 11, I think I've assigned those before. Either 13 or 15 or both. And any of the odds 17 through 29. Try to do any of the odds 31 to 37. Do 39. And then try to do any of the odds 41 to 47. Then writing a linear combination, that's what we were just doing. Either 49 or 51 or both. Okay, we'll stop there, and after we do example 7, then I can assign the rest of them, because that's the last that we'll be doing. All right, good deal. Any questions? So we'll pick up and go with that next time. Sorry about my throat. Goodness gracious.